Right. Well, then thank you for attending my talk. And I will be presenting joint work with Nicolas Tabareau about observational equality. So, as with every story, our story needs a place to start, and this place is Martinov type theory. MLTT is quite a sweet spot in the Curie-Howard correspondence between proofs and programs. Sorry. On the one hand, it is expressive enough to do a large part of mathematics and to define a lot of computable functions. But on the other hand, it is also very tractable, which makes it a great foundation for proof assistance. And it satisfies important properties such as decidability, which means that your computer will always be able to tell whether or not your proof is correct, and normalization and canonicity, which means that all the functions you defined will compute on data types. So you will never need a lemma to prove that 5 plus 5 is 10, for instance, or that foo of 7 is 42. It will always compute. However, the equality that is supplied by Martinov type theory is less than ideal. This is because it encodes the equality of programs and not the equality of behaviors, as is more common in mathematics. And why is that so? Well, this is because equality is a data type, so it must satisfy canonicity, which means that in the empty context, the only proof of equality is reflexivity, and so two equal terms have to be convertible. And since conversion is decidable, well, equality in the empty context will also be decidable. And while this might seem desirable at first, it also has some very severe consequences. The first is that there is no hope to have function extensionality. And the second is that there is no hope to quotient the type by an equivalence relation. But both of these constructs are actually ubiquitous in mathematics. So throughout the years, people have developed numerous workarounds, but all of them have their downsides. This is unavoidable, of course, because as we explained, the problem is a consequence of the rules of type theory, canonicity, and decidability. So any workaround must weaken at least one of these properties. And for instance, you could simply postulate the principles that you need, which is probably the most common in practice, but it does break computation even for the integers. You can also use setoids, but then you get a lot of boilerplate and you don't have a working universe anymore. You could also use modified type theory, such as extensional type theory, which is unfortunately not decidable, or cubical type theory, which is decidable, but does not compute very efficiently. And all of the homotopical prerequisites are a bit much for a general purpose proof assistant. So the workaround that interests me the most today is observational type theory. Altenkirch and McBride came up with it in the early 2000s to fix the problems of the intentional equality. In OTT, short for observational type theory, the built-in equality, which is called observational equality, is not an inductive data structure, as instead it is defined by recursion on the types and terms. For instance, if the user forms this equality, 2 is equal to 2 for the observational equality, which is written with the tilde, well, then the system actually notices that it is dealing with integers, so it will reduce by recursion on the terms. So first it will reduce to 1 is equal to 1, then to 0 is equal to 0, and then finally to true. Let's have another example. So for instance, if the user forms an equality between two inhabitants of a function type, well, then the system will actually notice it too and reduce it in one step to basically what is the statement of function extensionality. And this is how we get that property. So this is the main idea of observational type theory. And now let us define our very own flavor of observational type theory, which is dubbed TTobs, sorry. And yeah, we will define it as an extension of Martinov type theory. So first, let's fill in the details about our first insight. Because it is not enough to explain how the equality is defined, we also have to explain how to use it in proofs. And since it is not a data type, of course, you cannot reason by pattern matching on it anymore. So how do we prove P of n if we know that n is observationally equal to m, and we also have a witness T of P of m? Well, the answer is typecasting. We introduce a new primitive that does coercions between two observationally equal types. And now we can use it to get our proof. Because since we can prove that functions do preserve observational equality, well, we know that P of m will be equal to P of n inside the universe. And then we can cast our witness of P of m into a witness of P of n. All right. And as with observational equality, cast computes by recursion on types and terms. For instance, in that example, the system sees that the source and destination of the cast are both function types. So it will do one step of reduction to this sort of back and forth function. You can see that this function takes any x inside of A prime, and then starts by casting it to A, applying f to it to get something inside B, and then casting it back to B prime to obtain, well, something in the desired codomain. But then you might ask, how do we know that we can actually form the casts that are involved? How do we know that A prime is equal to A and B prime is equal to B? Well, remember that in TTobs, equality types compute. So in particular, the type of E, which is an equality between two arrow types, two function types, will reduce to a product of two equalities, the first between A and A prime, and the second between B and B prime. And then we just use first and second projections to get our desired equality proofs. All right, but typecasting is quite a bit less powerful than pattern matching because we cannot use it to reason about the equality proofs themselves. So for instance, it is impossible to prove reflexivity or transitivity just with cast. So this is where the second insight of observational type theory comes in. We need a layer of proof-irrelevant types that will actually contain the observational equality. Now, any two proofs of observational equality will be convertible, which means that the system cannot tell them apart anymore, and they don't have any computational content either. Therefore, we can get a Streicher axiom K by definition. And this also allows us to freely add some non-computational axioms in the proof-relevant layer, because it does not break computation in the proof-relevant layer. Because, well, after all, there is no computation at all in the proof-irrelevant layer in the first place. So we can freely postulate the properties of equality, since it lives in the proof-irrelevant layer, and its properties such as reflexivity, etc. So, finally, we will need one third piece of insight to handle indexed inductive types. Regular inductive types, such as integers, dependent pairs, or lists, work just fine in the presence of observational equality. However, indexed inductive types are a bit different because they will need a supplementary constructor. This is actually unavoidable since we can get non-canonical inhabitants from function extensionality and typecasting. So, for instance, we can still define the inductive equality, and it will becomes this term, this inductive type, I mean. So now it has a supplementary constructor that allows us to build an inductive equality from the observational equality, which is written eccast. So the inductive equality will actually satisfy function extensionality now, since we can get it from, the observational equality. However, do note that in spite of the supplementary constructor, the J eliminator remains untouched. To eliminate the inductive equality, it suffices to provide the case for reflexivity, and it will satisfy the computational rule on REFL, so reflexivity, and the rules for cast will be automatically inferred. So with all of this, we have a proper extension of Martinov type theory that validates extensionality principles such as function extensionality, the equality of co-inductives being bisimulation, proposition extensionality for the proof-irrelevant propositions, and of course axiom K. But we cannot have every single extensionality axiom because the most important and well-known one is univalence, which we cannot have simultaneously with axiom K. So now that we laid the groundwork of TTobs, we can extend it with supplementary types, such as irrelevant squash types and relevant box types to go back and forth between the proof-relevant and proof-irrelevant layers. Also subset types, such as, for instance, the type of integers that are smaller than 10, or quotient types, but only by a proof-irrelevant equivalence relation. So let me explain how we handle these quotient types. We can do some very simple quotient types as follows. They are constructed by giving a type along with an equivalence relation, which is in the proof-irrelevant layer. We obtain then a canonical projection that I called pi, that allows us to construct element of the quotient type from elements of A. And then we also get an eliminator that I did not spell out fully because it is quite cumbersome, but it does exist. And then we can define the obvious reduction rule for the observational equality, which is that the equality of two canonical projections reduces to the relation R. So this works nicely and this does get the job done, but there might be a more natural way to incorporate this quotient into the scheme of inductive types to actually have quotient inductive types, which would be nice, but we haven't really thought about that yet. So, well, everything is very nice, but not particularly new, because everything we said could actually be pieced together from the various articles, blog posts, and whatnot of McBride and his co-authors. Our main contribution is actually a proper meta-theory for TTobs, because we will prove consistency, normalization, canonicity, and decidability of type checking. And this does show that all of these additions do not break the crucial properties of Martinov type theory, and the only price to pay is some weakened canonicity result for the indexed inductive types. So first, consistency. Well, this one is the easiest. We just want to ensure that there is no way to prove that 0 is equal to 1. And this part is not too difficult, as it suffices to construct a model using setoids. So this can be done either in type theory or in a set theory, as long as we have enough logical power to define the universe. For instance, we can use induction recursion or some classical reasoning using ordinals and stuff. From there, we obtain that we cannot prove absurd statement in the empty context, and we cannot prove either equalities of anti-diagonal terms inside the universe, by which I mean that the only type that can be equal for the observational equality to a function type is another function type where the domain and codomains are equal. So now let us turn to more interesting properties, namely normalization, canonicity, and decidability of conversion. These are proved with the logical relations, as usual. And since the rules of TTobs are actually quite complex, because for now I only showed you the non-dependent rules, but trust me, the dependent rules get much worse. We used the Agda framework of Abel, Eumann, and Vetsozy to do a formal proof of these three properties. So this is proved in the Agda proof assistant. So not only this confirms that this framework is very usable to do concrete reasoning about new type theories, but it also proves that the logical power of TTobs is pretty much the same as with Martinov type theory. So for the experts, let me point out some interesting points in the proof. So first, note that we have no computation in proof-irrelevant propositions at all. So any inhabitant of a proposition will be reducible as soon as it is well typed. So we cannot hope to have any sort of canonicity result for proof-irrelevant propositions. But since we can get inhabitants of any type from a proof of false, which is a proof-irrelevant proposition, we can have a priori non-standard integers. So we have to rely on canonicity. No, sorry, we have to rely on consistency to actually prove canonicity for the integers. And of course, the consistency result comes from our model. And finally, reducibility of cast relies on having an inductive description of reducible types. And this does work in the context of inductive recursive logical relations that we used. However, this seems kind of incompatible with reducibility candidates, which are the standard method to handle impredicativity. So the question of whether TTobs is compatible with proof-relevant impredicativity remains open. Now, quickly a word on semantics. Well, of course, observational type theory does compute on type. However, this does not mean that universes can only contain syntactic type. Sorry, this does not mean that semantic universes can only contain syntactic types, because indeed we have no type-rect operator in our theory. So all that matters is actually that universes are closed under the usual type constructors, just as with Martinov type theory, and that they do not confuse functions that have distinct codomains and domains, which is a new constraint, which is not present in Martinov type theory and comes from the observational equality. Still, this allows for a very wide range of models, and such as, for instance, shift toposes, for which TTobs might actually be a very good language. However, please do note that proof-irrelevant impredicativity is standard in the formulation of elementary toposes, and it is not present in vanilla TTobs. However, since it is talking about proof-irrelevant impredicativity and not proof-relevant impredicativity, I think it is not very hard to add, and it can be shown to be to preserve normalization and canonicity. And finally, a word about implementation. The good news is that it is not too difficult, because all in all, we only need 3 ingredients. The first one being definitionally proof-relevant types, which are already featured in Coq, Agda, and Lean. The second one being 2 primitives, cast and the observational equality, along with adequate rewriting rules. And the third ingredient being a new constructor for indexed inductive types. So as an experiment, we use Jesper Koch's rewrite rules to implement TTobs in Agda. And it does work, but it is quite slow because of the nature of rewrite rules and their implementation. But there are plans to add it as an option to the Koch kernel in the near future, so please stay tuned for that. And this is the end of my talk, so thank you, and I will be happy to answer questions if you have some. me switch back to this thing. Maybe I should stop sharing and answer questions.
If you see the local one, then I'm going to. Your test corresponds to original version of OTT, observational type theory, but do you also have the equivalent of the coherence law that casting is the identity, or can it be the driver?
So actually, since the statement of that casting is the identity is proof irrelevant, we can just postulate it freely. Since, well, it is an axiom, but it lives in the proof irrelevant layer. So we just assume it, and this does not pose any problem with computation. So, yeah. Could you give an example of a non-canonical term that causes you to need the extra cast constructors for indexed type? Well, you can just, in the empty context, use function extensionality to derive a proof of observational equality of two complex functions from integers to integers. And then you can use cast to transform this proof of observational equality into a proof of inductive equality, which will necessarily be non-standard because equality on functions between integers are not decidable. Hopefully, this answers the questions. The question. Sorry. So
not just for equality.
What is the intuitive idea? There is a lot of echo. If someone could cut his mic, it would be nice. Thank you. So what is the intuitive idea behind the extra constructor for indexed inductives and what they might look like in general, not just for equality? So the intuitive idea is just to freely add one constructor that builds values from cast. So in general, if you have some very complex indexed inductive type, it will just have one more constructor that takes a proof of equality between two instances of the indexed inductive type and an element of the first of these two indexed inductive types, and the intuitive meaning is that it is supposed to be an element, a non-canonical element of the second indexed inductive type that is obtained by casting the element of the first one along the equality. And then it just commutes with basically everything that computes, and everything works nicely.
Question. Very nice work. Thank you for taking an interest in it. If we have squashing and quotient by craft relations, isn't quotient by set relation definable?
So of course, it is definable. This is very right. However, the only thing that will not hold is that you can get back to the set relation from a proof of equality inside the quotient type. Like, for instance, if you build your quotient type using truncation, or squashing, whatever, then you will, if you have an equality between inside the quotient, then you will only be able to extract a proof of the squashed set relation and not the full set relation. And this is unfortunately completely unavoidable when we have proof irrelevant equalities. And to my knowledge, the only workaround is to work with basically univalent type theory.